See, this is the synchronous FIFO. Okay, in this we are designing the FIFO design code. This is the design code. See what we are seeing here. So module name is synchronous FIFO. This is a parameterized design. What we are taking the parameters here? Parameter width, data width is 8, so that is the width of your bus, and then depth is 16. Okay, how many entries you want to do in FIFO, that defines the depth. Here 16 entries I am doing here, and then address width equal to C log 2 of depth. What is the depth here? 16. So 16 placed here, 16 can be written as 2 power 4. Then address width is 4. Okay, and then these are the signals: clock, reset. For write interface I need write enable, and then write data, that is also parameterized. So based on the data width is 8. So 8 minus 1, 7 down to 0, that is an 8-bit data. And then I'm checking the output is full. Okay, while doing the write operation I need to check the full, and then while doing the read operation I need to check the empty. And then so there is another count. So how many items you have written into your FIFO, that will be the counting here. See, internal memory I am taking FIFO memory. So width down to 0 down to 0 to with depth minus 1. That means 0 to 15 it is doing that. Okay, 0 to 15 means 16 count, 16 operations it is doing that. So depth means FIFO depth, so 1, 2, 3 and so on, so 16 counts it will be doing that. And then width is 8-bit width. Okay, and then write pointer, read pointer, I need to check that how many writing operations are doing that and reading operations are doing here. So then write pointer and read pointer, it is automatically incrementing, depends upon your data. Okay, and then flag operation like full, when FIFO count is reaches to your depth means it is full, and then FIFO count is 0 means it is empty. And then I need to check the FIFO count here. FIFO count equal to count. So whatever the count we have, that will be assigned to count. And then write operation we are doing. This is the asynchronous reset we are taking. Passage clock or passage reset. Begin. If reset, during reset condition write point equal to 0. If it is exit from the reset, and then we are checking that write enable and not full. Full is not full condition, and then write enable should be 1. Then it begins that. The write data should be stored in your FIFO. Okay, so write data is stored in write pointer. Based on that FIFO memory I have taken, that is the width of 16 bit. Okay, the data will be stored in FIFO memory. Okay, based on the write pointer. So write pointer equal to write pointer, that is should be equal to depth minus 1. Your depth is 16. 16 minus 1, 15. So starting from 0 to 15. So when it is equal to depth count, that means write pointer is incrementing up to the depth. Okay, whenever it is reaches to depth minus 1, then it is empty. Sorry, full condition. Okay, so that is full condition, or it increments the write pointer by 1. If it is not true, it increments the write pointer 1 time. If it is true means your write pointer is reaches to full condition, and then it will exit the condition. Similarly, read operation. Always flip flop at the rate passage clock or negate passage reset begin. If it is reset, read point should be 0. And else begin. What is the condition? Read enable and not empty. So if both the condition not empty and then read enable are incrementing, so it is also checking that read point equal to read pointer is equals to depth minus 1. If it is equal to depth, then your entire data will be khali. Okay, So then we are getting 0. If it is not empty means then your read pointer will be incrementing. Okay. So then before output I am checking here read data equal to, we have already written the data here where we are writing write data equal to FIFO memory of read write pointer. Similarly, I have stored the data into my FIFO memory. So that data I want to get the data. Okay, that data I want to retrieve it. So that is the FIFO read operation. Read data equal to FIFO memory of read pointer. Okay, read pointer it will get the data from that. And then always a flip flop, passage clock and the passage reset begin. If reset FIFO count equal to 0 and else begin. See how the FIFO count is managing. So it will check that. See, four conditions it will check that. Case write enable and not full, comma read enable and not empty. So these two conditions are true means if it is taking, so 1 0 means, so this is 1 and this is 0. Okay, this condition is 0 and this is 1. Then FIFO count equal to FIFO count plus 1. Then write operation is doing that, and 0 1 means read operation is doing that. Okay, both are 1 means your count should be incrementing. So FIFO count equal to, so FIFO count. Default condition is FIFO count when you are doing no operation. Okay, it is doing read write operation, it will be incrementing the count. Okay, same thing here we are executing the test bench, Verilog test bench. This is Verilog test bench. So how we are testing this condition? So check this condition. Just tick time scale module, your TB name, and then parameters. What are the parameters we have taken? Same parameters are also considered here. And then your TB doesn't have any input output ports. All are logics only. Okay, logic and then clock, reset, write, enable. All the signals are represented here. And then DUT instantiation. Your DUT synchronous FIFO instantiation here. After that, clock generation. So this is the clock generation, and then so and then taking that idle condition, drive to idle condition, all are equal to 0. Okay, and then I'm checking that do write operation. Write operation means a write enable equal to 1, read enable should be 0, and write data we are giving that. After some time, I'm disabling that write enable write operation. Similarly, do read operation. Write read operation we are doing that. After that, task automatic when you are doing that simultaneous operation. That means doing write operation as well as read operation. Both write and read equal to 1. So value should be write value equal to write data and read data equal to read value. Okay, so we are doing the write read operation continuously, and then task automatic check count. So how many counts you are doing that? If count is equals to expected, count is not equal to expected, then we are getting that dut dot count here, dollar display error in your count. Otherwise it is expected means else begin count will be incrementing, and then else begin condition we are checking that. So else begin condition what we are checking, dollar display it is count is matching. Okay, I am receiving the count is matching here, not equal to means error we are getting. Otherwise we are receiving expected data. And then similarly check empty condition. Empty condition, empty is not equal to expected. Here also error condition we are getting. Otherwise error count will be increasing. And then else begin we are checking that. So we are checking that your data is empty or not. And similarly check full. Full we are checking. Full we are checking, and then check read data. So read data and write data we are checking that. So read data, write data, full, empty, all conditions we are checking. So then initial begin, I am writing the test case here. So synchronous before depth and width. So I have written that. And then it is during initialization, that means during reset condition all are equal to 0. After 3 clock cycles, and then I am releasing that reset condition. Then I am checking that test reset state, basic write operation, basic read operation, FIFO full, FIFO empty, and then wrap around simultaneous read write operation, overwrite of protection, and underflow protection, random operations. All these 10 test cases we are checking here. So first test case. So I'm displaying the condition, test summary, total test count, and then error count. So after that, if error count equal to 0, your test is passed. Otherwise, your test is may get error and then fail. Then check that first condition, reset condition. During reset condition, all are zeros, right? So then test count is incrementing, and then test count equal to checking the reset state test count. At that time, check the empty. Empty, I need to make a 1. That means that is not an empty. And then full 0. Okay. So and then that is not full, and count is also 0. So all are checking that. So full equal to 0 means it is not full. Okay. And then it is empty is 1 means your FIFO will be empty, and then count is 0. So that is reset condition. We are checking that. And then basic write operation. Write operation, during that write operation, do write, we are doing that. That means I am placing data here. Okay. Write operation, it is doing that, right? See, write data and FIFO memory, we are placing that. Then AA is keeping your data, and then read queue push back. AA is you are pushing one data, you are pushing. After that, I'm checking that empty is not condition. Empty condition is not, so not 0, not 1. That means not empty. One data you have written, and then count is incrementing. Check that basic write operation is completing. One test count is incrementing. Similarly, same AA data, I'm reading that data. Where you are pushing the data, right? Now I'm copying the data. So then basic read operation, actual data, test count is incrementing, read operation is doing that, and expected data equal to read queue dot pop friend. Whatever the queue is there, we are copying the data. That means I'm getting the data. And then do read actual data. If it is actual data is not equal to expected data, you are getting the error. Otherwise, I'm getting the matched data, expected data. So similarly, FIFO empty condition, FIFO full condition, we are checking that. Okay. FIFO full condition, how we are checking that FIFO full condition here? This is the fill FIFO completely. How many operations it is doing that? 15 operations. Then for loop we are checking for I equal to 0, I less than depth, and I plus plus. Do write operation. Okay, it will do the write operation up to the depth condition. Up to 16 operations it is doing that. Then push back condition of read data. It is doing the read operation. If checked, if it is true means check the full condition F1, and then count is incrementing up to depth. So then similarly, empty condition, empty the FIFO. Now I am decrementing. You are pushing the data there, and you are popping the data up to the FIFO depth. Okay. So then expected actual data is equals to expected data, not equal to expected data, we are getting the error. Otherwise, we are receiving that empty condition is 1, count is 0, and then FIFO empty will be 1 here. And then wrap around condition. So that means again I'm going back to first condition. Okay. So that is the wrap around condition. Suppose I'm reaching the first half of the condition, read half values, and then again wrap around them. 8 values are reading, and again going to first. Again other 8 values are reading. Then total 16 values are reading here. And then write cause around. After that, read all and verify it. So that means all the data we are reading or not, and simultaneous read write operation, same writing and reading. One data is writing, one data is reading. That can be checking here. And then overwrite protection, that means after pulling after pull of your FIFO, still you are writing the data. Okay. So that is the overriding condition, override condition. And then after empty that, you are still getting the data from the FIFO. That is the underflow, overflow, underflow, and randomly. So randomly I am checking the different conditions. Okay. So now I am executing this one. We are getting the data or not? Just check that. See, all the tests are passed. 10 tests are passed, 0 errors. expected data, so all are getting here. See, first test FIFO empty condition, actual data value is 0, 1, expected data is 1, actual data is 1. And then FIFO full condition, expected data is 0, actual value is also 0. Okay, so we are checking the actual values and expected values. So write operation, expected is AA, actual is also AA. Okay, and then read operation, same data I need to get that, right? So before full condition we are checking that expected value is equal to 16, actual value is also 16 condition. Okay, so one condition we are doing that, and then FIFO empty condition, both are zeros here. And then um, testing pointer wrap around, that means 16 conditions we are doing that, and then actual values, that means 8 reads and 8 writes are doing, right? Same thing we are doing here. And then simultaneous read write operation, expected data is 86 HCC0, and then 8 tick HC0. Okay, so that means one write operation, after that one read operation. Okay, underflow overwrite protection. Overwrite protection means after reaching the 16 data, still you are executing the data. So that means FIFO full condition, and then FIFO empty condition, and then expected values are also 1 here. Okay, so this is basic FIFO condition, and then Verilog and design test bench. Okay, normal test bench. Now we are checking that UVM test bench. Okay, in this same, first I am writing that interface here. So all the design code I have placed here, same code. Okay, same code that is also working. Now we need to check with the design is working with your UVM test bench or not. So I'm checking here what we are checking. So FIFO interface, in the interface what are the input output signals are there, all the signals we are placing here, right? So logic, reset, write enable, read enable, write data, read data, full, empty, and count. All the signals are placed in the interface. After that we need to import the package. For import the package, so import UVM package scope resolution star. That means whatever the package you have, that will be importing here. Okay, and then macros.sh. Okay, and then these two steps are common for everyone. Okay, and then UVM analysis implementation codes, you are checking that actual data, and then analysis implementation declaration codes for reference model. Okay, actual value and reference model, so both are equal means your test is passed, otherwise you are getting some fail condition. See, all parameters we are placing here, parameter int before width, before depth, and then data width, before depth, address width we are placing. And then test cases, what are the classes we are having? FIFO item, that means sequence item, driver, monitor, sequencer, agent, reference model, scoreboard, coverage collector, environment, base sequence. After that, write sequence, read sequence, concurrent write read operation, overflow test sequence, underflow test sequence, reset sequence, base test, reset test, basic test, and overflow test, underflow test, random test, and concurrent test. What are the sequences are there? All sequences we are writing the test cases. Okay, reset sequence is there here, right? Where is this? Write sequence, FIFO base sequence, read sequence, concurrent, overflow, reset, all this. Then reset test sequence, base test, reset test, basic test, and then overflow test, underflow test, random test, FIFO, concurrent test. All the tests we have written. After that, in the package, we are implementing that. After the package declaration, then we go for uh, sequence item. Class FIFO item. FIFO item is my class name, extends from UVM sequence item. Class registration. Take UVM object details FIFO item. Okay. So and then type def read write reset operation we are doing that. That way type def we have considered, read data operations we are doing here. And then what are the signals available here? So clock, reset, and then write enable, read enable, all the signals we have placed here. So what is the randomized data? Rand bit write data in. Okay, data out, data in and data out. We are taking here, and then full empty condition. After that, count increment. For that, we are doing some valid operations like based on the constraints. Operation distributional constraints I am taking here. Reading is 40%, writing is 40%, and reset is 20%. Equal read write operation. After that, reset operation it is doing that. And then function write. This is the custom constructed function new string name FIFO item. Sequence, right? For the sequence only string name is only available. There is no even component parent. And super dot new name and end function. So this is the conversion. Your string to convert your function is some string that should be converted here into some decimal format or any other format. Okay, so $s format f operation percentage less operation dot name. What is your operation? So that should be placed here, and then read operation we are doing that. So $s format data out equal to percentage 0h hexadecimal data we are writing, and read operation is doing that write operation and reset operation. All the signals will be displaying in your $s format f. See, do copy. We are doing do copy means we are writing the code manually. Okay, if you write copy method means the code is automatically takes them. Do copy, do compare, do means we are writing code manually here. And FIFO items, what is the handle? RHS. Okay, RHS is my FIFO handle, and then dollar if not dollar cast of RHS comma RHS, that means we are upcasting here. Okay, and doing the upcasting, and then it will do that do copy dollar cast is failed. If you get an error, dollar cast is failed, return that. Otherwise, super dot do copy, we are doing the some operations. What operations are doing? Operations equal to RHS dot operation data in data out full empty count. All the signals are handling by the RHS handle. Okay, function do compare. Do compare, it is doing that same similarly. So it will do that. If it is not comparing, then I'm getting the error value. Otherwise, I'm getting the comparison value. Do compare RHS comma comparer, and what is the operation? Operation equal to RHS dot operation and data equal to RHS dot data in. All the signals we are mentioning here, and then I'm ending the sequence item here. It is copying, and then comparison operation is doing that. And then base sequence. What is the UVM sequence is my parent class, and then here it is a parameterized with sequence items or FIFO items, and then base sequence is your child class. Class registration, pick UVM object details, UVM FIFO base sequence, and then function new FIFO base sequence here written. In the body method, pre-body method, what I am doing here, we are checking that is that starting phase equal to null, and then start that phase rise objection. In between the phase rise and drop objections, I am creating the sequence, creating start item, and then randomization, and then reset the item and finish item. Okay, so UVM handshake mechanism. All the handshake mechanism steps are writing here. After the task post body method. This is pre body method and post body method. So in that post body method, if start phase is not equal to null, then phase rise should be dropped. Okay, here phase is raised here, and phase should be dropped here. In between the rise and drop, we are sending the items and then finishing the items. Okay, creating start item, and then randomization and finish item. Okay, so that is the basic test here. And then FIFO write sequence extends from UVM base sequence. From the base sequence, I'm doing write operation here. Okay, same thing. Class registration, number of transactions I'm taking here. If the number of transactions inside the 1 to 20, because we are doing 16 operations. So 16 count, that's why 1 to 20 it is taken. And then custom constructor, function dot new, function new, string name, super dot new, name comma pair name, and then end function. In the body method, what we are doing, FIFO item, whatever the FIFO item we are taking, that is the handle for transaction, and repeat number of transactions. That means 1 to 20 transactions it will be repeating. After that, create the object for this. Okay, I am creating the object tr equal to FIFO dot FIFO items, create type ID, create transactions. In that start item, after that randomization, in this randomization I am doing the write operation. Okay, so I'm taking that inline operation, inline constraint operation is equals to FIFO items, and then scope resolution write operation. Okay, so it is doing the write operation, then it will randomize that. Otherwise it is not randomizing, and we are getting some error here. After that, if it is not getting error, finish the items. Okay, so this is write sequence. Similarly, read sequence, same thing. Number of transaction is 1 to 20, so function name, and then class for custom constructor writing, task body method, same FIFO items, repeat for number of transactions, and then class registration, memory creation, object creation, and then start items, same thing. We are doing the read operation here. Okay, in doing the inline operations, randomize transaction dot not randomize with operation is equals to FIFO items read. Okay, if all items are read means not doing the randomization and getting the error. Okay, if it is not doing the error, and then I am finishing the items and ending my read sequence. Write read is happening. After that, concurrent write read sequence. One write and one read. Same thing. See, virtual task body, repeat number of transaction, created the object here, start item, doing the write inside. Inside what? Read and write. Okay, in between that, read write operations are doing. Concurrent read write operations are doing. Previously only read and only write. Now read write operations are doing here. Similarly, overflow test. Overflow test means same thing. We need to write that after reaching the depth plus 3. See, so how many times it is repeating? We are checking that. Before depth is 16. Then it is added plus 3. That means we are exceeding that before depth. Then creating the object here, start item, and then before write operation we are doing here. If it is not getting, then error we are getting. After that, finish item. Okay, same underflow test. That means we are previously we have added some other test cases. So transactions are added, extra transactions. Now we are decreasing. Okay, transactions. So task body method. So create the item, transaction, create item, start item, and doing the read write operation with write operation. Okay, underflow test, right? Underflow test means so writing below the depth, that is the underflow. Okay, so randomization failure, finish item. So how many times it is repeating after write operation? If not done, then FIFO read operation we are doing that. Okay, FIFO read operation up to the empty, and then doing the read operation. So after empty also we are doing the read operation, that is the underflow operation. Okay, so repeat of 5 times. See, here repeat of 3 times. We are doing the write operation 3 times, but here doing 5 times. That means 3 times we need to do that, but extra another 2 times we are reading the data, but there is no data. Then we can check that underflow is happening or not. Okay, and before reset test. Reset test means we are checking all the items should be equal to 0 or not. See, uh, repeated the item handle we have created, repeat 4 times, create the object here, start item, and then doing the write operation here. After that, again creating the item, start item, reset. After writing, you are doing the reset. That means all are equal to 0. Then repeat 2 times, you are doing the read operation. After reset, is that doing read operation? No, we need to get the randomization value. Okay, and then FIFO driver code. What is the, see, all sequences are completed, then we are writing the driver code. We need to drive the signals. So class FIFO driver, your class name extends from UVM driver. This is also parameterized because sequence items we need to transfer through driver. Okay, and then class registration TQM component utils FIFO driver, virtual FIFO interface. So FIFO interface I am representing with virtual. Okay, FIFO depth comma FIFO depth comma data width VAF, because parameterized class, right? So that's why we are taking the width and depth here. And then class custom constructor. After that, build phase. In build phase we are getting the config db here. So UVM config db virtual interface, virtual FIFO interface. Your class name is virtual, your interface name is virtual FIFO interface, that is the int type. Hash FIFO depth comma width, and then get, this means for this component, and empty means globally we are applying that. What is your interface handle? VAF. The string name is VAF, and then instance name is VAF. Okay, value is also VAF. If it is not getting the config DB, we are getting that error. So no VAF, virtual interface must be set for that get full name comma VAF. So we are not getting the VAF. Okay, if it is getting means this error is not getting. In the task run phase, virtual task run phase, UVM phase. So FIFO items, we are creating the handle for that sequence items, that is the items. Okay, all are initialized to 0. So during reset condition, all are initialized to 0. And then forever begin. What is the handshake mechanism? Sequence item code dot get next item, and then case items dot operation. We are doing the operations: write operation, read operation, and reset operation. So first operation FIFO items write. If you are doing the write operation, write enable equal to 1, read enable is 0, and then write data is equals to items dot data in. So at the rate of clock age, so at the rate of passage clock, we are doing the write enable equal to 0. After doing all the write operation, we are keeping that, we are driving that write enable equal to 0 after one clock cycle. Similarly, read operation. During that write enable equal to 0, read enable is 1, and then items dot data out equal to VF dot read data. Okay, so virtual, from the virtual interface we are getting the data here, because here you are writing the data through virtual interface into your write data. Now VF dot read data equal to items dot data out. Okay, so based on that you are doing the read operation, and during reset condition, after that read operation, then read enable should be equal to 0. Okay, it is exit from the read operation. Now we are checking the reset condition. During reset condition, write enable, read enable, and reset all are so write enable, read enable should be 0, reset should be 1. After 3 clock cycles, and then repeating 3 times, next time we are asserting that reset value equal to 0. That means releasing that reset condition. Then we are checking that full and empty conditions here. Items dot pull equal to VF dot pull, VF dot empty equal to items dot empty, VF dot count equal to items dot count. Then we are completing your driver code. After that, we are observing it. So driver is driving that codes to DUT. Then we can observe what the DUT responding. Okay, how the DUT is responding, we need to check that. Class FIFO monitor extends from UVM monitor. Take UVM component details, that is class registration. After that, virtual FIFO interface, same interface we are getting that. So because transactions items are keeping in your virtual interface. Now from virtual interface to some monitor, what we are doing, it will collecting the data from pin level data to packet level data, it is converting. Okay, monitor is converting that, and then virtual interface we are taking here. After that, analysis ports we are implementing. that means item collected ports. Okay, from the DUT we need to collect that items. That will be passing through scoreboard. Okay, custom constructor. This item collected port we are creating the memory here by using new method. And then body method in build phase we are getting the config DB. Both steps are common for driver and monitor. Only this IUVM analysis ports are implemented here. Okay, in the driver is not there. Config DB is there, and then custom constructor is there, virtual interface is there, all the things are there. Okay, available. After the task run phase, what we are driving the data. So during reset condition, after one clock cycle we are creating the memory. After the creating the object, after creating the object we are checking that reset condition. During reset condition, current items dot full equal to FIFO dot full. Okay, vf dot full, vf dot empty. Okay, so previously we are assigning that vf, now vf to normal items we are assigning that. Then item collected dot write method, we are implementing write method here. Write method during reset also implemented, and also a write method we are implementing in so during write operation. Okay, and then during read operation also we are implementing that write operation. Okay, so same thing will be applied here. See, during write operation what we are doing here, else begin. So if wf dot write enable and not full, then we are creating the memory. After that we are checking that items dot write operation, and then current item dot data in equal to vf dot data in. Okay, vf dot write data. So vf dot write data we are driving through sequence items that will be assigned to same data input. So your data input and then data write output both are same, your test case is matching, otherwise we are getting some fail condition. Same during write operation is completed, and then read operation write enable and vf dot empty condition. Empty conditions we are checking them here. Full condition, empty condition, count and item collected port that current item we are writing. Okay, so that means counting how many write operations you are doing, and what is the empty condition, what is the count we are checking there. Similarly, write vf dot read enable and vf dot empty. So then not vf dot empty. Then we are doing the read operation here. During the read operation, what we are doing here, current item dot data out equal to vf dot read data. That means only data we are getting that. From the vf dot data, we are assigning the data output, and then checking the all conditions. Sequencer we know that just class and custom constructor ends there. That is the sequencer shortest code. And agent, driver, sequencer, monitor we are connecting in your connect phase, because custom constructor virtual function build phase. In that build phase we are creating the um, object for monitor, and then it is a passive, so only monitor is there. If it is active, driver and then sequencer also there. Okay, so after creation of the object, then we will go for connect phase. We are connecting that driver dot sequence item port dot connect sequencer dot sequence item export. That means driver, sequencer, sequence and driver we are connecting that. How the sequencer is connected to driver we are checking that driver dot sequence item port dot connect sequencer dot sequence item port dot export. Similarly, reference model we are creating that. Reference, based on the reference model we are checking that. So how we are implementing the reference model? Same FIFO items comma reference model EVM analysis ports, and then analysis port FIFO items comma reference output port. Okay, same similar to scoreboard type. So constructor we are creating the memory for that reference item port dot and reference count. In the write method we are doing the data FIFO reference, FIFO items reference item, creating the object here. After that creating the object, case reference operation, that means reference operation we are doing that. Okay, so reference item dot operation, what is the operation we are doing? Write operation, and then read operation and reset operation. Same thing we are doing here. Okay, so during write operation, what we are checking, pushing the data into that reference FIFO. Reference FIFO we are creating that reference FIFO items, and then we are taking that FIFO items. Both are equal means it is passing. In scoreboard we are writing that. Okay, same thing. FIFO read items. We are popping the data. FIFO reference FIFO dot pop print, and count is decrementing. Here count is incrementing. While doing write operation, it is incrementing the count. While doing the read operation, it is decrementing the count. Then reset operation all are 0. Then empty condition reference count equal to 0. Full condition reference count equal to 15, FIFO depth, and then FIFO items count equal to reference item count equal to FIFO count. So these are checking with items empty, item full, and item count. So before that reference is there. Same thing we are checking on the scoreboard. Reference model is written. The scoreboard, same analysis implementation boards, that is the actual implementation boards, and then UVM analysis reference boards, implementation of reference model. FIFO items come up, FIFO scoreboard, and then reference implementation boards. So this is the actual codes, this is the reference boards. Okay. So actual queue we are taking, and reference queue is also taking. Count all the counts are equal to initialized to 0. That is the statistics we are writing. After that custom constructor we are creating the memory for that actual and reference count. Okay. Function void write actual FIFO items, and then create the items. Copy items. We are doing the copying the items. Okay, so where you are copying CPY, we are doing the copy. Then actual queue push back to copy. So compare the items. So here pushing the copy items, whatever the items are there in that actual copy, actual queue is there. In that actual queue, what you are copying the data, that whole data is placed into actual queue. Then I am comparing the items. So we are doing the comparing items. Same thing. Function void write reference. So reference model we are writing, creating the item, and then copy items reference queue, and push back to reference queue. So here actual queue, and then here reference queue. Now I am comparing that. In the comparison logic, function void compare items. So FIFO items, actual items, reference items. If actual q dot size greater than 0 and reference q dot size is also greater than 0, okay, so it is doing the write operation, and then checking that actual count and then reference counts. Okay, and then actual items is equals to actual q dot pop print. We are getting the data, and then reference item equal to reference q dot pop print. The count is incrementing. If you are doing that read operation here, then actual items dot data out equal to references items dot data out. So reference item data and then actual data both are equal, and then reference dot empty, actual dot empty, reference item dot empty, and items full, reference items full, actual items count, reference item counts, all are equal means I am getting the read match. Otherwise read mismatch will be getting. Count is incrementing, mismatch count is incrementing, and then I am getting the mismatch. Similarly write operation. So what we are taking, actual items dot empty, reference items dot empty, and actual items dot full, reference items dot full, actual items dot count equal to reference items dot count, all are checking, and then match count. If it is that, right matching is happening, otherwise right mismatch is going on. Similarly reset condition. Okay, this is your actual scoreboard, and then I am writing the report phase. Okay, after that UVM FIFO coverage collector. Coverage collector, what we are writing? So class your FIFO coverage collector extends from UVM subscriber, and then class registration, FIFO items, item, and into FIFO label. How much labels we are writing? What is the cover group here? Items operation we are doing, that is one operation. Items operation write, read, reset. During cover point, items dot empty condition, bins empty equal to 0, not empty equal to 0. Okay, empty condition I am checking that. Similarly items dot full, means fill equal to 0, fill equal to 1, not full equal to 0. So full it is means I'm checking that full value 1. If it is not full means not full equal to 0. Okay. And then FIFO level. What is the FIFO level we are taking that? That means empty condition 0 and meet condition 1 to depth minus 1, full condition FIFO depth. Okay. FIFO depth, up to the FIFO depth it is reaching means your FIFO is full. And then operation empty cross, that means cross operation, that means right operation cover point is there, operation cover point is there, and empty cover point is there. And similarly full condition, operation dot cover point is there and full cover point is there. Okay, for these two cross operation we are doing that. And then memory creation, after that function void write method we are checking that reset condition, write condition, and read condition. Okay, reset condition all are equal to 0. And then full condition, write condition, FIFO full and not full and item labels. And then if that is equals to less than or equal to FIFO depth. And then FIFO level is incrementing, and similarly read operation, not empty, FIFO level is greater than 0. Here less than FIFO depth, here greater than 0, and FIFO level should be not equal to, so it is decrementing. If it is negative value means it is exit the condition. So after that sampling the conditions, then environment. During environment, we are connecting all the components. Item collected port dot connect reference model, agent dot monitor dot item collected port dot connect scoreboard dot actual analysis ports, actual ports, and reference model we are connecting agent dot monitor dot item collected port dot coverage analysis export. Okay, so all the connections we are doing in environment phase. After that, test cases. What type of test cases? UVM FIFO base test. This is the base test. We are checking that. In that base test, what we are writing, function void build phase. We are getting the config DB, and then setting the config DB here. After that, virtual function end of elaboration phase. So UVM top dot topology, we are getting that. After before the starting simulation, any adjustment we need, end of elaboration phase will take care of that. Task run phase, phase dot rise objection, drop objection, we are writing the test case. Similarly, reset test. So phase dot and rise objection, we are creating the idea and then start the sequence. So where we are starting sequence dot start dot environment dot agent dot sequencer. From the sequence environment to sequencer, we are connecting that. Similarly, FIFO basic test extends from UVM base test. Basic test, we write sequence, read sequence, and then phase write drop objections we are writing here. Okay. So this is write operation, and this is for read operation. During write read operation, we are getting that number of transactions is equals to FIFO depth. So then your reading will be completing. Okay. And here we are also doing that number of transactions up to FIFO depth. Your writing is completed. Okay, here count is incrementing, here count is decrementing. Overflow test. So just incrementing the condition. Sequence item dot, where we are incrementing sequence and then creating the item. So how many times we are repeating here? Phase dot rise objection, sequence dot start. Okay, your test is starting. And then FIFO dot underflow test. Underflow test we are checking that. Okay, and then random test, concurrent test, all the test items we are checking that. In the top module what we are writing, so package, parameters, um, DUT instantiation. Okay, so after that clock generation, and then initializing all the signals and display, setting the config db here. Okay, so you will config db setting, and then you are running the test here. So run test, see I'm testing all the cases, run test, before random test, basic test, and before reset test, before overflow test, all the tests I am running here. Okay, just run here. For that we need to check the languages, system verilog UVM 1.2, and then tools are used that Synopsys VCS tool or any other tool. Okay, something we have changed, right? Control check. So previously something we have changed. Now it is done. Okay. Okay, size. So 555. Okay, size greater than 0. So now we can see the test case reports here. So UVM top FIFO random test is executed. The value is ID is 341. Okay, and then FIFO environment is executed, agent and then driver analysis ports. See how we are checking that number of integral request is 30. Okay, last request is 1 and then last response also 1. Okay, so this is the report we are seeing now. In the run test we can change that. Okay, this is copy, this can be copied here. So just comment this one and write another test case name. What is the other test case name we have? FIFO base test. Can we execute this? Sorry, reset. FIFO reset test. So during reset operation we are checking FIFO reset test. Save and run this one. Okay, so it is executed. So before reset test is also executed in the top module and then all the reports are same. Okay. Similarly, you can test all the test cases.